Strain gauges mounted on the surface of a loaded machine part were aligned in the direction of principal stresses and gave the following values for the strains. Epsilon 1 is equal to 0.0021 and epsilon 2 is equal to minus 0.00076. Take Young's modulus of elasticity is equal to 207 gigapascal and Poisson's ratio is equal to 0.292. So here it is a common data question. It consists two questions. The first question is calculate the principal stresses acting on the surface. Options are 325 megapascal minus 28 megapascal, 225 and minus 38, 425 minus 33.2, 52.5 and minus 18 megapascal. Sorry, this is 525 and minus 18 megapascal. And the second question is if the principal stress in the third direction is equal to 0, then the normal strain produced in that direction is here minus 3.34 into 10 power minus 4, minus 4.34 into 10 power minus 4, minus 5.53 into 10 power minus 4 and 0. So coming to the solution, here they gave directly the principal strains, that is epsilon 1 and epsilon 2. From that principal strains we can get directly principal stresses by using the equation sigma 1 is equal E into E1 plus, let us say this is epsilon 1 plus mu into epsilon 2 by 1 minus mu square, where epsilon 1 is equal 0.0021 and epsilon 2 is equal to minus 0.00076, where mu is equal to Poisson's ratio and is given by 0.292 and E is equal to Young's modulus of elasticity and is given by 207 gigapascal, that is 207 into 10 cube megapascal or Newton per mm square. Megapascal. Now substitute all the values in the equation, then we get a value of principal stress, that is sigma 1. So here sigma 1 is equal to 425 megapascal. And now second principal stress sigma 2 is given by E into E2 plus mu E1 by 1 minus mu square. So here already we know the values. So it is epsilon 2 is epsilon 1. Let us say sigma 2 is equal to E into epsilon 2 plus mu into epsilon 1 by 1 minus mu square. So again substitute all the values. So all the known values, so that we get here sigma 2 is equal to minus 33.2 megapascal. So here sigma 2 is equal to minus 33.2 megapascal and sigma 1 is equal to 425 megapascal, and in the options correct answer is C. First correct answer is C for first question. Now consider the second question. So we'll have to calculate the principal strain in the third direction, and in that direction principal stress is equal to 0. Now the principal strain in the direction, let us say epsilon 3 is given by sigma 3 by E minus mu into sigma 1 plus sigma 2 by E. So which is equal to, here sigma 3 is 0 minus mu is equal to 0.292 and sigma 1 is 425 and sigma 2 is 33.2 by E is equal to 207 into 10 cube, which is equal to minus 5.53 into 10 power of minus 4. So this is the answer for second question, and in the option the correct option is C. C is the right answer. Hot fluid of specific heat 2000 joule per kg Kelvin enters a parallel flow heat exchanger at a rate of 2.77 kg per second and is at 200 degrees centigrade. It is to be cooled by a fluid entering at 25 degrees centigrade with a mass flow rate of 0.69 kg per second, and specific heat of the fluid is 4000 joule per kg. Overall heat transfer coefficient based on outside area of 20 meter square is 250 watt per meter square Kelvin. It is a linked answer question. It consists two questions in a way such that the second question answer depends on first question answer. Here the first question is effectiveness of the heat exchanger is 0.5, 0.4, 0.62 and 0.82, and the second question is calculate the exit temperature of the hot fluid, and the options are 100 degrees centigrade, 123.6, 145.6 and 196 degrees centigrade. First we will have to find out effectiveness, and effectiveness of the parallel flow heat exchanger is given by 1 minus e power of minus n2u into 1 plus c by 1 plus c, where n2u is the number of transfer units and c is the ratio of minimum heat capacity to maximum heat capacity of the fluids. So here first we'll have to find out the heat capacity of the both the fluids. First consider hot fluid. So the hot fluid specific heat is given by 2000 joule per kg Kelvin, and mass flow rate of the hot fluid is given by 0.77 kg per second, and the total heat capacity of the hot fluid is equal to the product of mass flow rate into specific heat of the hot fluid, that gives 0.77 into 2000, and which gives a value of, sorry, it is 2.77, so which gives a value of 5540. So this is the heat capacity of hot fluid. And now consider the cold fluid data having specific heat of Cp is equal it is 4000 joule per kg Kelvin, and mass rate of the fluid is equal 0.69 kg per second. Now the heat capacity of the cold fluid is equal to the product of mass flow rate into heat capacity of the cold fluid. So it is equal to 0.69 into 4000, which gives a value of 2760 joule per Kelvin, and Ch also in joule per Kelvin. So these two are the heat capacity of hot fluid and heat capacity of cold fluid. So here we'll have to consider first minimum heat capacity of the both the fluids. Here the minimum capacity of the fluid for cold fluid, minimum capacity for the cold fluid, that is 2760 joule per Kelvin. Now calculate the number of transfer units that is given by UA by C minimum, where C minimum is the minimum heat capacity of the both the fluids, and here U is the overall heat transfer coefficient and A is the concerned area. Here overall heat transfer coefficient is given by 250 and area is 20 meter square by, and minimum heat capacity of the fluid is 2760, and which gives a value of 1.8. So here number of transfer units is equal to 1.8, and in the effectiveness formula we have C, that is the ratio of minimum heat capacity to maximum heat capacity, and C is equal to C minimum to C max. So that is given by 2760 to 5540, it is nearly equal to 0.5. Now consider the effectiveness formula, which gives 1 minus e power of minus 1.8 into 1 minus 0.5 by 1 plus 0.5, so it gives a value of 0.62. So here the effectiveness of the heat exchanger is equal to 0.62, and 0.62 is the right answer in the options. The correct option is C. C is the right answer for first question. And coming to the second question, it will have to calculate the exit temperature of the hot fluid, and again from the epsilon or effectiveness of heat exchanger, we can write it as Ch into Thi minus Th out, that is the cold fluid temperature at the inlet minus hot fluid temperature at the inlet minus hot fluid temperature at the outlet by C minimum into hot fluid temperature at the inlet minus cold fluid temperature at the inlet. So it gives a value of, which is equal to a 0.62, and from this equation we can write as 5540 into 200 minus, we will have to calculate the exit temperature of hot fluid, and C minimum is 2760 into 200 minus 25, which is equal to, from this equation, the hot fluid temperature at the exit is equal to 145.6 degrees centigrade. And in the options, the correct option is C. C is the right answer for the second question also.